What shoes do to a sprint? Spikes, trainers, and bare feet. When athletes sprint, footwear is doing more than protecting the feet. It changes how the athlete interacts with the ground, how long each foot stays in contact, how frequently the athlete steps, and how forces are transmitted during acceleration. For a sprinter, these differences can matter. A fraction of a second can separate competitors. But footwear may also change the mechanical demands placed on the body during training. So what actually happens when the same athletes sprint barefoot, in regular running shoes, and in sprint spikes? That was the question examined by Xiao, Nagahara, and Fuchs in a study of competitive sprinters. Previous research had already shown that sprint spikes can improve performance, while barefoot running tends to change variables such as step frequency and ground contact time. But there was an important limitation. Most biomechanical studies had examined only a one or a few steps. That matters because acceleration is not one uniform movement. During the first few steps of a sprint, an athlete is moving relatively slowly and trying to accelerate rapidly. As speed increases, body position, contact time, step length, and the forces applied to the ground all change. A footwear effect observed near the start may therefore be quite different from one that appears 20 or 30 meters later. To investigate this, the researchers studied 17 highly trained male sprinters. Each athlete completed 60-meter sprints barefoot, in regular running shoes, and in sprint spikes. Importantly, these athletes were accustomed to all three conditions. The unusual feature of the experiment was the running track itself. 50 force plates allowed the researchers to follow the athlete's interaction with the ground across the entire acceleration phase, rather than examining a single isolated step. The clearest performance result was perhaps unsurprising. The athletes were fastest in spikes. Their average 60-meter time was 7.58 seconds in spikes, compared with 7.70 seconds barefoot and 7.73 seconds in regular running shoes. In sprinting, a difference of around 1/10 of a second is far from trivial. But what is more interesting is how the three conditions produced different ways of reaching high speed. Barefoot sprinting produced a particularly rapid stepping pattern. The athletes took more steps per second and spent less time on the ground than they did in regular running shoes. These differences were not restricted to one moment in the sprint. Higher step frequency in the barefoot condition was especially persistent across the acceleration phase. Regular running shoes produced a different pattern. Ground contact tended to last longer, and the athletes generally produced less propulsive force than they did in spikes. One possible explanation concerns cushioning. A cushioned shoe deforms when the athlete hits the ground. That can help distribute forces, but the authors suggest that it may also delay how quickly force is transmitted. At sprinting speeds, where contact with the ground may last only around 1/10 of a second, even small changes in force transmission could matter. Sprint spikes appear to solve a different problem. They're designed for traction and relatively stiff force transfer. In this study, the athletes produced the greatest propulsive forces and impulses in spikes. In simple terms, they were better able to direct substantial force into pushing themselves forward. Interestingly, they also produced greater braking forces. Braking occurs when the foot initially contacts the ground and some horizontal force acts opposite to the direction of travel. So spikes did not simply reduce every mechanically undesirable force. Instead, they increased both braking and propulsion. The overall result was still better performance, suggesting that the additional propulsion outweighed the additional braking. This is an important reminder that sprint mechanics cannot always be reduced to a rule such as less force is better or more force is better. What matters is how force is produced, in which direction, and at what stage of the sprint. And that brings us to perhaps the most distinctive finding of the study. Most footwear differences were not constant. They appeared and disappeared as the athletes accelerated. For example, the advantage of spikes in step length became particularly evident during the middle and later parts of acceleration. Differences in propulsive force also depended on how far the athletes had progressed through the sprint. Ground contact differences changed as speed increased. In other words, asking which footwear produces the best sprint mechanics may be too simple a question. The answer may depend partly on the distance being sprinted. That is especially relevant outside track and field. Many team sport athletes repeatedly sprint for distances well below 40 meters and may never reach their maximum running speed. Footwear designed for these athletes could therefore benefit from being optimized for the mechanical demands that occurred during acceleration rather than for maximum speed sprinting. There are also possible implications for training. Barefoot sprinting generated a distinctly different mechanical pattern, with shorter ground contact times, higher step frequency, and generally lower horizontal forces than sprinting in spikes. That makes barefoot work potentially interesting as an occasional training variation rather than as a replacement for sprint footwear. The authors suggest that varying footwear could expose athletes to different mechanical demands, and barefoot exercise might potentially help develop foot function while encouraging rapid stepping and short contact times. But this should not be interpreted as evidence that barefoot sprinting prevents injury. The study did not measure injuries, and lower ground reaction forces do not automatically mean lower stress on every structure in the body. Likewise, the larger forces observed in spikes do not necessarily mean that spikes are harmful. The body can redistribute and absorb forces in different ways. There is another important qualification. These were highly trained male sprinters who were already accustomed to barefoot running, running shoes, and spikes. The same responses should not be automatically expected in recreational runners, team sport athletes, or people who suddenly begin sprinting barefoot. So the practical message is not simply that spikes are fast, running shoes are slow, or barefoot training is better. The more useful message is that footwear changes the strategy an athlete uses to accelerate. Spikes supported greater horizontal force production and the best sprint performance. Barefoot sprinting encouraged faster stepping and shorter contact with the ground. Regular running shoes produced yet another force and contact time profile. And importantly, these effects changed as speed increased. For coaches, athletes, and footwear designers, that means sprint distance matters. The best shoe and the most useful training condition may not only depend on how fast someone needs to run, but also on which part of the acceleration process matters most. For more detailed information, please consult the full-text article or contact Philip X. Fuchs from National Taiwan Normal University.